Download this code from codegive.com, link in the description below. Don't count your chickens before they hatch, a guide to responsible programming with code examples. The proverb "don't count your chickens before they hatch" warns against being overly optimistic about future success based on uncertain or incomplete information. In programming, this translates to avoiding premature assumptions and planning around results that haven't yet materialized or are potentially unreliable. Premature optimization, anticipating the best-case scenario, and relying on untested or unstable components are all forms of counting your chickens in the coding world. This tutorial explores these pitfalls and provides practical examples in Python to illustrate how to avoid them. The essence of premature optimization, a performance chicken counter. Premature optimization is the act of optimizing code before you know where the actual bottlenecks are. It's spending time and effort making a part of your code faster when that part isn't actually slowing down the overall performance of your program. Donald Knuth, a pioneer in computer science, famously said, "Premature optimization is the root of all evil, or at least most of it, in programming." Why is premature optimization harmful? Wasted effort. You might spend hours optimizing code that has a negligible impact on overall performance. This time could be better spent on more critical areas or on improving the code's clarity and maintainability. Increased complexity. Optimization often involves making trade-offs that increase code complexity. This can make the code harder to understand, debug, and maintain. It also increases the risk of introducing bugs. Incorrect assumptions. You might optimize based on assumptions about how the code will be used or what data it will process. If these assumptions turn out to be incorrect, your optimization efforts could be wasted or even detrimental. Hindered readability. Complex optimizations can significantly reduce code readability. Clear, understandable code is often more valuable in the long run than slightly faster, obfuscated code. The correct approach: measure, then optimize. The key is to identify the actual bottlenecks in your code before attempting any optimization. This requires profiling and measuring the performance of your code to pinpoint the areas that are consuming the most time or resources. Example: Python, a prime number generator. Let's consider a simple example of generating prime numbers using a naive approach and then see how we can prematurely or correctly optimize it. Now, imagine we think the append operation is the bottleneck. We might be tempted to pre-allocate the list. This is a premature optimization. In this example, pre-allocating the list might not significantly improve performance and might even make the code less readable. The actual bottleneck is likely the is_prime_naive function itself, which iterates up to n1. A more effective optimization: square root check. A better optimization involves checking divisibility only up to the square root of n. This drastically reduces the number of iterations required. Using a profiler. For more complex code, use a profiler to identify the performance bottlenecks. Python offers built-in profiling tools like cprofile and line_profiler. The profiler will show you which functions are taking the most time, allowing you to focus your optimization efforts on the most impactful areas. Key takeaways for premature optimization: 1. Measure first. Always profile your code before optimizing. 2. Identify bottlenecks. Pinpoint the areas that are actually slowing down your code. 3. Optimize judiciously. Focus on the most impactful bottlenecks and avoid unnecessary complexity. 4. Test thoroughly. Ensure that your optimizations don't introduce bugs. 5. Prioritize readability. Don't sacrifice code clarity for marginal performance gains. 2. The perils of best-case scenario programming. expect the unexpected. Don't count your chickens also applies to assuming that your code will always encounter the ideal or best case scenario. Real-world applications often deal with unexpected inputs, network errors, resource limitations, and other unforeseen circumstances. Planning only for the happy path leads to fragile code prone to crashing or misbehaving when faced with adversity. Common mistakes * ignoring error handling * failing to handle exceptions, example file not found error, type error, value error, gracefully. * assuming data validity * not validating user inputs or data retrieved from external sources. * ignoring resource limits * not accounting for memory constraints, disk space limitations, or network bandwidth limitations. * overlooking concurrency issues * assuming that your code will only be executed by a single thread or process. Example, Python file processing. Let's consider a scenario where we're processing a file. Why is this problematic? Without the try except block. * file not found error * if the file doesn't exist at the specified path, the program will crash. Value error * if a line in the file doesn't conform to the expected CSV format, example missing commas, invalid data types, the program will crash. Unicode decode error * if the file contains characters that cannot be decoded using the default encoding, the program might crash. *OSERror, or subclasses file system errors, permission issues, or disk errors can occur during file access. Improved version with robust error handling *. The try, except block gracefully handles potential exceptions. File not found error * handles the case where the file doesn't exist. Value error * handles errors related to incorrect data format. Exception as a general catch-all exception to handle any unforeseen errors. It prints the error message, allowing for debugging and preventing the program from crashing abruptly. Beyond basic exceptions, input validation. It's essential to validate user inputs and data retrieved from external sources to prevent unexpected behavior. This example demonstrates type checking *instance, data, list, verifies that the input is a list. Length checking len, data, equals 3 ensures that the list has the expected number of elements. Data type conversion with error handling attempts to convert the data elements to floats within a try, except block to handle potential value error exceptions. Raising custom exceptions raise type error, and raise value error, allow you to signal specific errors with informative messages. Resource limits and defensive programming. Always consider resource limits. For example, when reading large files, avoid loading the entire file into memory at once. Use iterators or generators to process the file line by line or in chunks. When dealing with external APIs, implement retry mechanisms and rate limiting to avoid overwhelming the service. Key takeaways for handling unexpected scenarios *. 1. Anticipate failure * think about all the ways your code could fail. 2. Use exception handling * wrap code that might raise exceptions in try, except blocks. 3. Validate inputs * check the validity of user inputs and data from external sources. 4. Handle resource limits * account for memory, disk space, and network bandwidth limitations. 5. Implement retry mechanisms * for unreliable operations like network requests, implement retry logic. 6. Log errors * log errors to help with debugging and monitoring. 7. Fail gracefully * avoid crashing the program. Provide informative error messages or attempt to recover from errors. 3. The illusion of stable dependencies. the chicken coop is only as strong as its weakest beam. Relying on the stability and reliability of external libraries, APIs, or systems without proper safeguards can be another form of counting your chickens. Dependencies can change, become unavailable, or introduce bugs that affect your code. A well-designed application handles these potential failures gracefully. Potential pitfalls ****. API changes ** external APIs can change their endpoints, data formats, or authentication methods without notice. Library updates updates to third-party libraries can introduce breaking changes or new bugs. Network outages network connectivity can be intermittent, preventing your code from accessing external resources. Database downtime databases can experience downtime due to maintenance or failures. Strategies for mitigating dependency risks version pinning specify the exact versions of your dependencies in your project's requirements file, example requirements.txt in Python, to ensure that your code uses the same versions across different environments. This prevents unexpected behavior caused by newer, potentially incompatible versions. Example, requests == 2.28.1. Dependency management tools use dependency management tools like pip, conda, or poetry to manage your project's dependencies and create reproducible environments. Abstract dependencies with interfaces define abstract interfaces for interacting with external systems. This allows you to easily switch to alternative implementations if a dependency becomes unavailable or unreliable. Implement fallback mechanisms provide fallback mechanisms to handle situations where a dependency is unavailable. This might involve using a cached version of the data, switching to a backup server, or providing a simplified version of the functionality. Testing write unit tests and integration tests to verify that your code interacts correctly with its dependencies. Mock external dependencies during testing to isolate your code and simulate different scenarios. Example, Python using an API with a fallback. In this example, API call with timeout the requests.get, API_URL, timeout equals 5, call sets a timeout to prevent the code from hanging indefinitely if the API is slow or unavailable. Exception handling *try, except block handles potential requests.exceptions.request exception errors, such as network errors, connection errors, and timeout errors. Fallback to cache if the API is unavailable, the code attempts to load data from a local JSON file, weather_cache.json. This provides a fallback mechanism to display cached data. Caching mechanism the API response, if successful, is cached to the local file. This ensures that the fallback data is available the next time the API is unavailable. File not found handling the inner try, except file not found error handles the case where the cached data file does not exist. Abstracting dependencies with interfaces, illustrative example. This example shows how to abstract away a database dependency. Here, DataStore is an abstract base class defining the interface. Postgres DataStore and in-memory DataStore are concrete implementations. The process_data function works with any DataStore implementation, making it easy to swap out the underlying database. If PostgreSQL is unavailable, you can quickly switch to in-memory DataStore for testing or a degraded mode of operation. Key takeaways for dependency management *. 1. Pin versions *. Use version pinning to ensure consistent dependencies. 2. Use dependency management tools *. Employ tools like pip, conda, or poetry. 3. Abstract dependencies ** define interfaces to decouple your code from specific implementations. 4. Implement fallbacks * provide fallback mechanisms for when dependencies are unavailable. 5. Test thoroughly * write tests to verify the interaction with dependencies. 6. Monitor dependencies * stay informed about updates and security vulnerabilities in your dependencies. 4. Conclusion, cultivating a realistic mindset. Don't count your chickens before they hatch is a guiding principle for responsible and resilient programming. It encourages you to avoid premature optimization * focus on clarity and correctness first, then optimize only when necessary based on profiling. Anticipate failure * plan for unexpected scenarios and handle errors gracefully. Manage dependencies * use version pinning, abstraction, and fallback mechanisms to mitigate the risks of relying on external systems. By adopting this mindset, you can create more robust, maintainable, and reliable software that can withstand the inevitable challenges of the real world. Just as a farmer carefully tends to their crops, a good programmer cultivates their code with patience, foresight, and a healthy dose of skepticism. Remember, the best programs are not those that assume perfection but those that gracefully handle imperfection.